Hello guys, myself Gautham and welcome to Home Institute. In this session, we shall have a very detailed discussion of all the GATE PYQs related to MOSFET DC analysis. Well, this MOSFET DC analysis is all about determining the regions of operation of various transistors in any given circuit. And finally, we should be able to find the required currents and voltages. Okay. Also, more than the solution, of course, I will solve each and every problem, but you please try to pay close attention to my approach and also my thought process, because once you understand how to think about these circuits, then you will be able to solve any problem, and that should be the final goal in any learning process. And by the way, if you think the video is a bit slow, then you can always set the speed to 1.5x and then you can enjoy it better. So let's get started. So on the screen, you can see the first question. I'll just read it out. Again, please remember that when you read the question properly, that itself is like half the solution. So whenever you are reading the question, any question, please read it very carefully with all your attention and focus. Okay. In fact, in your mind, you can just read it out. Yes, you don't have to read it aloud, but within your mind, you can just read it. Okay. So when the gate to source voltage, that is what VGS, of a MOSFET with threshold voltage of 400 millivolts. So what is given? The threshold voltage is given, it is 0.4 volts working in saturation. So they already said that the MOSFET is operating in saturation is 900 millivolts. So what is this 900 millivolts? It is the value of VGS. Okay. So when the value of VGS is what 0.9 volts, that is what 900 millivolts, the drain current, that is what the value of ID, is observed to be 1 milliamp. So when VGS is what 0.9 volts, what is the value of the drain current? It is 1 milliamp, neglecting the channel length modulation effect. So they are saying that you can assume there is no channel length modulation. So if there is no channel length modulation, then the value of lambda is going to be at 0. Yes. And assuming that the MOSFET is operating at saturation, already it was given that MOSFET is operating in saturation. Okay, so the drain current for an applied VGS of 1400 millivolts. So what do we know about the MOSFET operating in saturation? Whenever there is no channel length modulation, ID will depend only on the overdrive voltage. In fact, ID is related to what? The square of the overdrive voltage. So you know ID is equal to what? Half mu n Cox W by L VGS minus VTH whole square. So from this, we can clearly see that in saturation, the drain current is proportional to what? The square of the overdrive voltage. Okay. Now in the first case, what is the overdrive voltage? VGS is what? 0.9, VTH is what? 0.4, and the drain current is what? 1 milliamp. Okay. And in the second case, the VGS is increased to what? 1400 millivolts. Okay. So what is the new VGS? It is 1.4 volts. Okay. So ID in the modified case will be proportional to what? 1.4 minus VTH, that is what? 0.4 whole square. And in the first case, the value of the drain current is what? 1 milliamp, and the value of VGS is what? 0.9. So 0.9 minus 0.4 whole square. You just have to divide the two equations. So ID divided by 1 milliamp will be equal to what? 1 square upon 0.5 squared, which is what, 4. So the drain current is what, 4 milliamps, which is what, option D. Okay. Let's move on to the next question. Again, let's read the question properly. The drain, that means what? The drain terminal of an N-channel MOSFET is shorted to the gate. You know, whenever drain is shorted to gate and if the MOSFET is on, the MOSFET will operate in saturation. Of course, VGS will be equal to VDS when drain is shorted to gate. The threshold voltage is what, 1 volt. If the drain current ID is what, 1 milliamp. Again, this problem is exactly same as the previous problem. Okay, so already because the drain is what, shorted to gate, the MOSFET will definitely operate in saturation. So here also you just have to rely on the fact that ID is proportional to what, VGS minus VTH whole square. Now in the first case, when VGS is what, 2 volts, the drain current is what, 1 milliamp, and in the second case, when VGS is 3 volts, what is the new value of the drain current? Okay. So first I'll write it for the second case, where the value of VGS is what, 3, and the threshold voltage is what, 1. So 3 ID is proportional to what, 3 minus 1 whole square. And then in the earlier case, VGS is what, 2. So 1 milliamp proportional to what, 2 minus 1 whole square. So again, ID divided by 1 milliamp is equal to what, 2 square by 1 square, which is again 4. So what is the value of ID? It is what, the same 4 milliamps. Is what, option D. Okay. Now for the circuit shown in the following figure, that is what, this figure. Transistors M1 and M2 are identical NMOS transistors. So they are saying that this one and this one both are identical transistors. Assume that M2 is in saturation. So this transistor M2, they are saying that it is operating in saturation. What about M1? If you look at M1, for M1, drain is shorted to what, gate. Whenever drain is shorted to gate, definitely the MOSFET will operate in saturation. Okay, and the output is unloaded and so on. The current Ix is related to I bias. Okay, what is this Ix? This Ix is nothing but ID2, the drain current of transistor M2. What is this current? It is 0, because for any MOSFET the gate current is what, 0. So what is this current? It is same as what, I bias. Okay, so what is this I bias? It is the drain current of M1. Okay, so I bias is nothing but ID1. So here the aspect ratios, nothing is given, which means you can assume every parameter is what, identical for both the transistors. So identical transistors operating in saturation will carry what, same current. Yes or no? Yes. Or you know, that result which is true for any current mirror, that is ID1 by ID2 is what, the ratio of the two aspect ratios, and here aspect ratios are equal, which means the ratio is what, 1. That means ID1 equal to what, ID2, which means Ix is equal to what, I bias. Okay, so this circuit, it is actually what, a current mirror. So the given circuit is simply what, a current mirror. Okay, please look at the next question. So this is what, the circuit. Consider the CMOS circuit. Why is it called CMOS circuit? Because this upper transistor is what, PMOS, and the lower transistor is what, NMOS. So there is also some type of CMOS circuit, where the gate voltage Vg of the NMOS transistor is increased from 0. So this Vg, initially it is what, 0, and then it is being continuously increased. Okay, while the gate voltage of the PMOS transistor is kept constant at 3 volts. That is what is also shown in the circuit diagram. Okay, so the gate of PMOS, it is at 3 volts. Okay, and it is held constant at 3 volts. Assume that for both transistors, that is for both NMOS and PMOS, the magnitude of the threshold voltage is what? 1 volt. That means VTM equal to mod VTP equal to what? 1 volt, and the product of the transconductance parameter and the W by L ratio. Transconductance parameter is what? That product mu times Cox. Okay, so they are saying that the quantity mu Cox W by L, product of the transconductance parameter, that is what? Mu Cox, and the aspect ratio W by L is what? 1 milliamp per volt square. That is for both the transistors, which means what? Both the NMOS and PMOS transistors, you can say they are equally strong, because mu n Cox W by L of NMOS is same as what? Mu P Cox W by L of PMOS. Okay, now what is the actual question? For small increase in Vg beyond 1 volt, which of the following gives the correct description of the region of operation of each MOSFET or each transistor? So what is the value of Vg? It is slightly increased beyond 1 volt. So you can say it is what? 1 volt plus some epsilon. Okay, where epsilon is what? A very small positive quantity. Look at this. So initially Vg is what? Less than 1 volt. Yes, I can say, because initially Vg is what? 0, and then it is being continuously increased. Initially Vg is what? 0, which is less than 1 volt. So if this is less than 1 volt, even this Vgs of NMOS will be less than 1 volt, which is less than the threshold voltage. Okay, that means initially NMOS will be off. What about PMOS? For PMOS, you know, we have to look at VSG. VSG of PMOS clearly is what? 5 minus 3, which is what? 2 volts, and it is more than mod VTP. That means what? PMOS is on. But whatever be the individual regions of operation, the two transistors, because they are connected in series, they should carry the same current. Okay, for example, if this current is what? IP, and if this current is what? IN, no matter what, IP must be equal to what? IN. So initially when Vg is what? 0, NMOS is off, so the current through NMOS is what? 0. If the current through NMOS is 0, then the current through PMOS also must be 0. Understood? Because both are in series, both should carry same current. If IN is 0, then IP is also what? 0. But for PMOS, the P channel is what? Formed. When will the drain current be 0 in spite of the channel being formed? Only when source and drain are at same potential. So for PMOS transistor, in spite of the P channel being formed, the current through PMOS should be 0, and that is possible only when the potential difference between source and drain is what? 0. That means because the source is at 5 volts, even the drain, that is the output voltage, must also be at 5 volts. Okay, well, this is as long as Vg is what? Less than 1 volt, and the NMOS is going to be off. But in our question, Vg is what? Increased slightly beyond 1 volt. Okay, so if Vg is what? 1 volt plus epsilon, I'll just clear this off. So what is Vg right now? It is slightly greater than 1 volt. Then what is the value of Vgs of NMOS? It is also 1 plus epsilon, which is greater than the threshold voltage. That means what? NMOS will turn on. NMOS will turn on. Okay, it starts carrying a small current. When NMOS turns on and starts carrying a small current, even the PMOS will start conducting, because PMOS is anyway already on. Yes. Now for the PMOS to start conducting, there has to be a potential difference between source and drain. Yes, earlier what was the output? It was what? 5 volts. Yes. Now a small current will start flowing through our PMOS. So for that there should be a potential difference between source and drain. Source will always be at 5 volts, so the drain should fall below 5 volts. Okay. You can say V0 will be what? Slightly less than 5, something like 4.9 or 4.95, something like that. Okay. So what is V0? It is some 5 volts minus epsilon 1. So what is Vg? It is slightly greater than 1. What is V0? It is slightly less than 5, but very close to 5. Okay. Now you should decide what are the regions of operation of the two transistors, that is what? NMOS and PMOS. Okay. So you can be systematic. So if you take PMOS, for PMOS, what is the drop between source and drain? It is what? Very small, because source is what? 5. Drain is also what? Very close to 5. Source and drain are nearly at the same potential. Then the potential difference between source and drain will be what? Really small. If the potential difference between source and drain is what? Really small, that particular PMOS transistor will definitely operate in triode. Okay. If you want, you can check the condition for PMOS to be in triode as well. What's the condition for PMOS to be in triode? I think Vd greater than Vg plus mod Vtp. Sorry. Vd greater than Vg plus mod Vtp. What is Vg for PMOS? It is what? 3. Mod Vtp is what? 1. So in other words, Vd must be greater than 4 volts for PMOS to be in triode. But for PMOS, what is the value of the drain voltage? It is very close to 5. Okay. Which will definitely be greater than 4. So PMOS will be in triode. PMOS will be in triode. What about NMOS? If you look at NMOS, for NMOS, what is the drop between drain and source? It is what? Almost equal to 5. Yes, which is a large potential difference between drain and source. If you have a large potential difference between drain and source, then most likely the transistor will be in saturation. If you have a very small drop between drain and source, then it is most likely in triode. Okay. But here, drain is what? Almost equal to 5. Source is what? Ground or 0. So drain minus source will be what? Very close to 5. If you want, you can check the condition for PMOS to be in, NMOS to be in saturation. Okay. So I'll just so for NMOS to be in saturation, you know the condition is what? This Vd must be greater than Vg minus Vtn. Okay. So for NMOS, what is Vg? It is slightly greater than 1, which is something like 1 plus epsilon, minus threshold is what? 1. 1 plus epsilon minus 1 will become what? Vd greater than epsilon. Vd greater than epsilon is what? Very small and close to 0. But what is our Vd? It is almost equal to 5. So anything which is close to 5 will definitely be greater than epsilon. So this condition is what? Satisfied. Even the earlier condition for PMOS to be in triode is also satisfied. So what is the final thing? PMOS will be in triode because of the small voltage between source and drain. NMOS will be in saturation because of the large voltage drop between drain and source. So NMOS is in triode, not really. Option D is correct. Option D, which is NMOS is in saturation and PMOS is in triode. So this is very much similar to what we have in a CMOS inverter. Yes, even in a CMOS inverter, yes, initially NMOS will be off and only PMOS will be on. As you increase the input voltage from 0, at some point when the input voltage exceeds the threshold voltage of NMOS, then NMOS will turn on and current starts flowing in the CMOS inverter. And when the NMOS turns on, it turns on in saturation and the PMOS operates in triode. So this circuit, it is not exactly the CMOS inverter, but in many ways it is similar to what the CMOS inverter. That much I can say. Okay. All right, moving on to the next question. In fact, this question, this question and the earlier question, both are kind of linked questions. Okay. So consider the CMOS circuit shown. So blah blah blah. This is all same as before. Estimate the output voltage V0 for Vg. So earlier, what was it? When Vg is slightly greater than 1, you had to decide the region of operation of each transistor. This time, for some particular value of Vg, you should find the output voltage. Estimate the output voltage V0 for Vg equal to what? 1.5 volts. Again, 1.5 volts is definitely greater than 1, but then not too far away from 1. Had it been 3 volts or 4 volts or even 5 volts, then you should rethink. Okay, but Vg, it's only 1.5, which is quite close to 1. Okay, when Vg is what? Close to 1, we know the regions of operation. NMOS will be in saturation, PMOS will be in triode. So we'll make, in fact, that is the hint given in the question itself. Okay, use the appropriate current based on the answer. Okay, anyway, so here we are going to assume that the NMOS operates in saturation and that the PMOS operates in triode. And then let's find the value of V0. In the end, we will check both the conditions so that you will come to know whether the assumption is correct or incorrect. Okay. So first and foremost, what is the value of VGS of NMOS? It is 1.5 volts. What is the value of VSG of PMOS? It is what? 2 volts. Okay. What is this current? Current through PMOS. Let's call it IP. What is this current? It is the current through NMOS. We'll call it IN. Okay. I already told you, because both are connected in series, the two currents have to be equal. IP must be equal to what? IN. Okay. Let's try to equate the two currents. Because PMOS is assumed to be in triode, what is the equation for IP? It is mu P Cox W by L of PMOS times VSG minus mod VTP times VSD minus half VSD square is equal to IN. IN is what? Current through NMOS, which is assumed to operate in saturation. So the expression for IN is what? Half mu n Cox W by L of NMOS times VGS minus VTN whole square. Now in the question, it is given that this mu Cox W by L value is what? Same for both transistors, which means this factor and this factor will get cancelled out. Only half will remain on the right hand side, apart from the voltage factors. Okay. Now, what is VSG of PMOS? It is what? 2 minus mod VTP is what? Threshold voltage is what? 1 volt for both transistors. 2 minus 1 times, what is VSD of PMOS? 5 minus V0. 5 minus V0 minus half into VSD square, which is half into 5 minus V0 square, is equal to half into VGS minus VTN whole square. VGS is what? 1.5 minus 1 whole square. That's all. So what is the only unknown in this equation? It is what? V0. But of course, you get a quadratic equation, which means you'll get two roots. By careful observation, you have to eliminate the invalid root. And then for whatever root you feel is what? Valid, you have to check the two conditions. Condition for NMOS to be in saturation and also the condition for PMOS to be in triode. Okay. But before that, you have to solve this quadratic equation and find the two roots. Okay. I'll just try to do it. So if I take LCM, what do we get? Ten minus 2 V naught minus 5 square is what? 25 minus V naught plus 10 V naught whole divided by 2. I think this 2 and this 2 will get cancelled out. 1.5 minus 1 is what? 0.5 squared, which is 0.25. Okay. So V naught square, there is minus 2 V naught minus 8 V naught. 10 minus 25 is what? Minus 15. We'll go to the other side. So if I am not wrong, this is the quadratic equation that we will get. Now you have to find the two roots of this equation. Just find it. So I would suggest you also do it along with me, okay? So the two roots are the following. V naught is what? 4.866 and V naught equal to what? 3.134. These are the two roots of this quadratic equation. Okay. Now you have to pick that value of V naught which will satisfy both the conditions. Okay, which will satisfy both the conditions. What is the condition for NMOS to be in saturation? VD greater than VG minus VTN, which is same as VD. VD is what? V naught. Okay, VD is same as what? V naught. VG is what? 1.5. So V naught must be greater than 0.5 volts. In fact, both the roots satisfy this particular condition. Now you have to look at the other condition. What is the other condition? PMOS must be in triode. For PMOS to be in triode, you know, VD must be greater than VG plus mod VTP. Again, for PMOS also the drain is what? Same as V naught. So V naught must be greater than 3 plus 1. In other words, V naught must be greater than 4. So these are the two conditions that must be satisfied. Yes, for this assumption to be true. One is what? V naught must be greater than 0.5. Another is what? V naught must be greater than 4. So what is the intersection of these two conditions? This one, V naught must be greater than 4. So clearly 3.134 is what? Less than 4, and this root is what? Greater than 4. So what is the value of V naught? It is 4.866. This 4.866 is same as what? I think 4 plus root 3 by 2. Again, that is what? Option D. I hope the thought process is clear. Okay. Moving on to the next question. In the circuit shown below, so this circuit contains what? Two MOS transistors. In fact, both are NMOS transistors. The value of mu n Cox is what? This much, 100 microamp per volt square. And the threshold voltage is what? 1 volt for both the transistors. The voltage Vx. So the voltage at this node is what? Vx at the source of the upper transistor. Okay. So this Vx, it is what? The source of the upper transistor. It is also the drain of the lower transistor. Okay. Maybe the arrow marks are missing at the source terminals. Okay. So what is this current? It is 0. So what is this current? It is what? 0. Let us call this transistor as what? M1. Let us call this transistor as what, M2. Let us call this current as what, I1. Let us call this current as what, I2. Again, from KCL, I1 must be equal to what, I2. If you look at M2, clearly drain is shorted to what, gate. Drain shorted to gate, transistor will operate in saturation. So M2 in saturation. Can we decide the region of operation for M1 as well? We can, because for M1 both the gate and drain voltages are given. We can check the condition either for triode or saturation. Okay. Let us check the condition for M1 to be in saturation. For NMOS to be in saturation, VD must be greater than VG minus VTN. Drain is what, 6, gate is what, 5, threshold is what, 1. So 6 greater than 5 minus 1, 6 greater than 4, which is indeed true. That means what? M1 also will operate in saturation. So already we know M2 is operating in saturation. Now we found that M1 also operates in saturation. Now we just have to equate the two currents. Okay. I1 equal to what, I2. What is this voltage drop? It is VGS of M1, which is 5 minus Vx. Okay. So VGS1 is what, 5 minus Vx. And what is VGS2? If this is Vx, then this is also what, Vx. Okay. And this drop is also what, Vx minus 0, which is Vx. So now we have both the VGSs in terms of Vx. What is the equation for the drain current in saturation? It is half mu n Cox W by L VGS minus VTH whole square. Okay. Since there is no mention of channel length modulation, etc., you can assume there is no channel length modulation. So what is I1? Half mu n Cox W by L 1 times VGS1 minus VTH whole square is equal to what? Half mu n Cox W by L2 times VGS2 minus VTH whole square. Okay. Now this mu n Cox half will get cancelled out. What is given about W by L1? W by L1 is what? W by L of M1 is what? 4. W by L of M1 is what? 4. 4 times. What is VGS1? 5 minus Vx whole square. What is W by L of M2? It is what? 1. 1 times. What is VGS2? It is Vx. Again, threshold voltage is what? 1. That's all. So from this equation, we can easily find the value of Vx. We can simply take square root on both the sides. So 2 times 5 minus Vx is equal to what? Vx minus 1. 10 minus 2 Vx. Correct. 10 minus 2 Vx is equal to what? Vx minus 1. Did I miss something? Well, I think this is correct. Okay. So 3 Vx is equal to what? 11. So Vx is equal to what? 11 by 3. So what is 11 by 3? It is 3.67 volts, which is option D. Okay. For the N-channel MOS transistor shown in the figure. So there is also what? An NMOS transistor. The threshold voltage VTH is what? 0.8 volts. Okay. Yeah. See, earlier problem I made a small mistake. VGS1 minus VTH, right? VGS1 is what? 5 minus Vx, and then minus 1 because VTH is what? 1. Now you take square root on both the sides, you will get 2 times 4 minus Vx is equal to what? Vx minus 1. 8 minus 2 Vx equal to what? Vx minus 1. 3 Vx equal to what? 9. So the correct value of Vx is what? 3 volts, which is what? Option C. Okay. So for this transistor, the threshold voltage is what given? Neglect channel length modulation. That means lambda is what? 0. When the drain voltage Vd is what? 1.6 volts. The drain current was found to be this much, 0.5 milliamps. And if Vd, that is the drain voltage, is adjusted to be 2 volts. So earlier the value of Vd is what? 1.6. Now the new value of Vd is what? 2 volts. And how did they change this value of Vd? Not by replacing the transistor, but by changing the values of R and Vd. So in both the cases, when Vd is what? 1.6, as well as when Vd is what? 2 volts, the transistor is the same. The values of R and Vd are different in the two cases. Okay. But what is common to the two cases, apart from the transistor being the same, in both the cases, the gate and drain are shorted together, which means in both the cases, the MOSFET will operate in saturation. So Vd is what? Voltage at the drain. What is the voltage at the gate? Because drain and gate are shorted, that is also Vd. So what is VGS? That is also Vd. So here, what is VGS? It is what? Vd. Okay. So in the first case, Vd is what? 1.6 volts. Then the drain current is what? Some 0.5 milliamps. In the second case, when the drain voltage is adjusted to be some 2 volts, what is the new value of the drain current? That is the equation. Because the MOSFET will operate in what? Saturation. You know, in saturation, the drain current is directly proportional to what? The square of the overdrive voltage. So ID is proportional to what? VGS minus VTH whole square. Okay. What is the value of VTH? It is 0.8 volts. Okay. So in the second case, Vd is what? 2. VGS is same as what? Vd. So 2 minus 0.8 whole square. In the first case, the value of ID is what? 0.5 milliamps, and the value of Vd or VGS is what? 1.6. So 1.6 minus 0.8 whole square. That's all. Usually you can find the value of ID. So ID divided by 0.5 milliamps is equal to what? 1.2 square divided by 0.8 square, which is 3 by 2 square. Okay. 3 by 2 square is what? 9 by 4. So what is the new value of ID? It is 0.5 milliamps into 9 by 4. .5 into 9 divided by 4, which is 1.125 milliamps. So what is the new value of the drain current? It is 1.125 milliamps. Okay. Look at the next question. This is a very good question. For the MOSFETs shown in the figure. So this is what? The circuit diagram. The upper transistor, it is what? PMOS, and the lower transistor, it is what? NMOS. So the circuit contains what? NMOS and a PMOS transistor. Okay. The threshold voltage mod Vt is what 2 volts. That means for both the transistors, both NMOS and PMOS, the magnitude of the threshold voltage is what 2 volts. So for this I can write Vtn equal to mod Vtp equal to what 2 volts, and this constant, that is half mu Cox W by L, it is what 0.1 milliamp per 0.1 milliamp per volt square, again for both the transistors. Okay, so can we say both the transistors are equally strong? Definitely right, because this value of mu Cox W by L is same for both the transistors. Okay, so here mu n Cox W by L of NMOS is same as what mu p Cox W by L of PMOS, and both are equal to what, this 2 goes to the other side. You can say it is what 0.2 milliamp per volt square. Okay. The question is what? To find the value of ID. In fact, this entire current is what? The drain current. So it is what? The drain current of PMOS. It is also what? The drain current of NMOS. So whatever ID that we are required to find is same as what? IP. It is also same as what? IN. Now let's do the analysis. First, you should decide whether each MOSFET is on or off, and if it is on, what is the region of operation, like triode or saturation. What is this current? Gate current 0. What is this current? 0. What is this voltage? Because this point is what? Connected to ground, there is what? 0. What is this voltage? It is what? -5. So what is this voltage drop? VGS of NMOS, 0 minus -5, which is what? 5 volts. Okay, so VGS of NMOS is what? 5 volts, which is greater than the threshold. That means what? NMOS is on. Now because this current is 0, these two currents will be equal. In other words, R1 and R2 will be in series. Okay, so from voltage division, what is the voltage at this point? 12 into 10 by 10 plus 10, which is what? 6 volts. And you know, for PMOS, we should always look at VSG, drop between source and gate. So what is the drop between source and gate? Source connected to what? 12, whereas the gate is at 6 volts. 12 minus 6 is what? 6 volts. So what is VSG of PMOS? It is what? 6 volts, which again is what? Greater than mod VTP. Okay, that means both transistors are on. But there is not the complete analysis. Now you have to decide what is the region of operation of each transistor. What is the condition or what is the constraint here? No matter what the individual regions of operation are, the two transistors, because they are connected in series, they should carry what? The same current. So already it is written here, IP equal to what? IN. Yes, so IP must be equal to what? IN. Already I told you that both are equally strong. Yes. Now which transistor has a greater this thing, what is it? Overdrive voltage. See, what is VSGP minus mod VTP? It is 6 minus 2, which is what? 4. What is VGSN minus VTN? It is 5 minus 2, which is what? 3 volts. So which transistor has greater overdrive voltage? PMOS has a greater overdrive voltage. Yes, and this overdrive voltage, is it not fixed? For both the transistors, the overdrive voltages are what? Fixed. Yes, for PMOS it is what? 4 volts. For NMOS it is what? 3 volts. For a transistor, whether it is NMOS or PMOS, for a given overdrive voltage, in which mode of operation the drain current will be maximum? I'll ask it again. If the overdrive voltage of a transistor is what? Fixed, then in which region of operation the drain current will be maximum? Is it not in saturation? Because if you go back to the plot between ID and VDS, the plot will be what? Like this, and then it becomes flat. Okay, So what is this? This is what triode. What is this? This is what saturation. So my question is what? In which mode of operation the drain current will be maximum? So clearly this is the maximum drain current and it occurs in saturation. Whereas if it operates in triode, then the drain current will be any of these values which is less than the maximum drain current. I hope you get this point. So for a given overdrive voltage, a transistor will carry maximum drain current when it operates in saturation, and a transistor will carry less than the maximum current when it operates in triode. Again, I'll repeat these 2 points. If the gate overdrive voltage is what fixed, then the drain current will be maximum in saturation, and the drain current will be less than that maximum value if the transistor operates in triode. Okay. So let's get this point aside and come back to this circuit. Now here we want both the transistors to carry what? The same current. Okay. Now let's say both are carrying what? Maximum currents. Yes, both are carrying maximum currents. Now will those two maximum currents be equal? Definitely not, because even though both are equally strong, see, when will maximum current flow? When transistor operates in saturation. For the time being, let us think that both are operating in saturation. NMOS and PMOS both are operating in saturation. Now the current in saturation is what? Half mu n Cox W by L of NMOS times square of the overdrive voltage. So the drain current depends on two factors. One is what? The strength. Another factor is what? The overdrive voltage. Now the strength is what? Same for both transistors, but the overdrive voltage is what? More for PMOS. So given that both are equally strong, and if both operate in saturation, which transistor will carry more current? PMOS will carry more current. I hope you get this point. So if both operate in saturation, then IP will be greater than IN. Okay. If both are in saturation, then IP will be greater than IN, because the overdrive voltage is greater for PMOS, whereas both are equally strong. IP will be greater than IN, but what is our requirement? We want IP to be equal to IN. So this IP equal to IN condition will not be satisfied when both operate in saturation. Yes. Now it is clear that one of them or both should not operate in saturation. Yes. At least one of them should operate in triode. Yes. Again, at least one of them should operate in triode, or maybe both can also operate in triode. But what is definitely true is what? Both cannot operate in saturation. Yes. Now in saturation the current will be what? Maximum. Yes. Let's say PMOS is in saturation, then PMOS will carry what? Maximum current. Now even if NMOS carries what? Maximum current by operating in saturation, still the current through NMOS cannot match the current through PMOS. So if at all PMOS carries what? Maximum current, it is impossible for the NMOS to match the current that flows through PMOS when the PMOS operates in saturation. So for the NMOS to be able to match the current through PMOS, the PMOS should carry what? Less than maximum current. PMOS should carry less than maximum current. Okay. So it's like there are two cars. Let's say there are two cars, car A and car B. Car A, the top speed is what? 100 kilometers per hour, and for car B, let's say the maximum speed is what? Only 80 kilometers per hour. And what is our requirement? We want both the cars to be traveling at same speed. Yes. So which car should not be traveling at maximum speed? Car A should not travel at maximum speed. If at all car A travels at maximum speed of what? 100 kilometers per hour, because car B can only travel at a maximum speed of 80 kilometers per hour, car B can never match the speed of car A. So car A should be traveling at a speed which is less than 100 kph. You understood? So here in our circuit scenario, this PMOS is like car A, NMOS is like car B, and we want both the transistors to carry the same current, or we want both the cars to travel at the same speed. So car A should travel at less than 100. Yes, in fact less than 80. Only then, less than or equal to 80, only then car B can match the speed of car A. So for the PMOS to carry less than maximum current, PMOS should operate in triode. Okay, PMOS should operate in triode. So all this discussion is only to arrive at the fact that PMOS cannot operate in saturation, because if PMOS operates in saturation, PMOS will carry maximum current and NMOS will never be able to match that maximum current, even if NMOS carries maximum current. Okay, because only the two strengths are matched, but the two overdrive voltages are not equal. Had the overdrive voltages also been equal, then both can happily operate in saturation, not at all an issue. Okay, so what is the thing here? PMOS should operate in triode. Okay, if PMOS operates in triode, what about NMOS? Yes, NMOS, should it carry maximum current, or NMOS also should carry less than maximum current? Anything is possible. Okay, again, if you go back to the earlier cars example, yes, even though the maximum speeds are what, 180, yes, both can travel at 50. Yes, 50 is less than 100, 50 is also less than 80, and the two speeds are equal. Okay, so now you have to decide whether NMOS operates in saturation or triode. But one thing is very clear, that PMOS should operate and will operate in triode. Okay, see. So this node, it is what the drain of both the transistors. This is what the drain of NMOS, it is also the drain of PMOS. Now because PMOS operates in triode, PMOS will definitely satisfy the condition for triode. So for PMOS to be in triode, what is the condition? I think VD greater than VG plus mod VTP. For PMOS, the gate is what, 6, mod VTP is what, 2. So even though we do not know the value of the drain voltage, for sure the drain voltage will be greater than 8. Okay, let us also write the condition for NMOS to be in saturation. For NMOS to be in saturation, VD should be greater than VG minus VTN. For NMOS, the gate voltage is what, 0, gate connected to what, ground. Threshold is what, 2. So VD greater than minus 2, but we already know VD is what, some value greater than 8. Anything greater than 8 will also be more than minus 2. So this condition is what, satisfied. That means what, NMOS operates in saturation. So what is the final thing? PMOS, it carries what, less than maximum current, and it operates in triode, whereas the NMOS, we found that it operates in saturation. Now the question is what, to find the drain current of any one of the two transistors. Either you can find IP or IM. So which one is easier to find? If you want to find the current through PMOS, then you should know what, not only VSG, you should also know VSD. But if you look at NMOS, which is operating in saturation, to calculate the drain current of NMOS, the only thing you should know is what, VGS, which is already known, that is what, 5 volts. Okay, so ID equal to what, IN, which is half mu Cox WL times VGS minus VTN whole square. Half into, what is mu Cox WL? It is 0.2 milliamp per volt square. What is VGS minus VTN of NMOS? It is what, 3. So I'll write 3 square. So 0.2 by 2. So this is what, volt square. Okay. So what is the value of the drain current? It is what, 0.9 milliamps. This is the final answer. So ID, that is the drain current, is what? 0.9 milliamps. I hope the thought process is clear. So always you have to look at what things like strength and then things like the overdrive voltage. Okay. For the MOSFET M1, that is this NMOS transistor shown in the figure, assume the aspect ratio W by L to be 2, the supply voltage VED to be another 2 volts, and the value of mu n Cox is what? This much, and the threshold voltage VTH is what? 0.5 volts. The transistor M1, that is this NMOS transistor, switches from saturation region to linear region when Vin is. So when does the MOSFET go from saturation to linear? What is the other name for linear? It is also called triode. So here they are asking what is the value of Vin, that is the input voltage applied at the gate, for which the MOSFET will go from saturation to linear. For this, if you simply recall the plot between ID and VDS, which is what? Like this. So what is this? It is VGS minus VTH. So to the right of this, MOSFET will be in saturation. To the left of this, MOSFET will be in triode or linear. So what is the boundary between the two regions? It is this. This we call it what? The edge of saturation. This we call it what? The edge of saturation. So in other words, what is the value of Vin for which the MOSFET operates at the edge of saturation? That is another way of framing the same question. What is the value of Vin for which our MOSFET will operate at the edge of saturation? So at the edge of saturation, the drain current is same as what? ID sat, and the value of VDS is what? VGS minus VTH. Yes, if VDS is what? VGS minus VTH. VD is what? At the edge of saturation, VD is what? VG minus VTH, and ID is what? ID sat. So there is the background that you should be able to recall for this problem. Okay. What is the gate voltage? It is Vin. What is the drain voltage? It is what? V out. And I am saying at the edge of saturation, VD is what? VG minus VTH, which is same as V out equal to what? Vin minus VTH, which is what? 0.5. Okay. So what is V out? It is Vin minus 0.5. This of course is what? ID. Then there is also what? ID. Yes. I'll just clear this entire thing. So what is ID? It is what? ID sat, which is half mu n Cox W by L VGS minus VTH whole square. What is this ID? It is not just the drain current, it is also what? The current through this 10 kilo ohm resistor. Ohm's law tells us that the current through 10 kilo ohm will be what? VED minus V out by 10K can be written as what? 10 power 4. Now let's substitute the different values. What is VDD? VDD is what? 2 volts, and V out is what? Vin minus 0.5 divided by 10 power 4 equal to half into mu n Cox is what? 100 micro. 100 into micro is what? 10 power minus 6. W by L is what? 2. VGS is what? Same as Vin. Again minus threshold is what? 0.5 whole square. So I'll try to cancel out a few things. So 10 power 4, 100, 10 power minus 6 will get cancelled out. 2 and 2 will also get cancelled out. So what do we get? 2.5 minus Vn equal to what? Vn minus 0.5 whole square, which is Vn square plus 0.25 minus Vn. Minus Vn will get cancelled out. Vn square equal to what? 2.25. So Vn is what? Plus or minus 1.5. So obviously this Vn cannot be negative, right? Because MOSFET has to be on. VGS must be greater than VTH. So Vn is what? This much, 1.5 volts. So what is the answer? It is 1.5 volts. Okay. Moving on to the next question. For the N-channel MOSFET, this is what the NMOS transistor in the circuit shown. Threshold voltage is what? VTH, and where VTH is what? Positive. Generally for NMOS transistor, the threshold voltage will be what? Positive, and for PMOS it will be what? Negative. And also the other thing you should notice is what? The gate and the drain are shorted together. So if at all this MOSFET is on, this MOSFET will operate in saturation. The source voltage, what is the source connected to? This battery, which is VSS, and the value of the voltage source VSS is varied from 0 to VED. Okay. Neglecting channel length modulation, again lambda is what? 0. The drain current ID as a function of VSS. So 4 options are given. In every option, ID is plotted versus VSS. You have to pick the correct option. Okay. So when VSS is varied from 0 to VDD, how does ID vary? How does the drain current vary? So for that you just have to look at VGS. What is the voltage at the gate? Gate is shorted to drain, which is connected to what? VDD. Just so VGS is what? VDD minus VSS. Okay. Now for MOSFET to be on, VGS must be greater than VTH, or VSS must be less than VDD minus VTH. VSS, that is the voltage at the source, it should be less than VDD minus VTH. Okay, it should be less than VDD minus VTH, then only the MOSFET will be on. So when VSS is what? Greater than VDD minus VTH, the MOSFET will be off and your ID will be 0. Okay. So if you look at the first option, beyond VDD minus VTH, what is the drain current? It is what? 0. Okay. Even in the fourth option, beyond VDD minus VTH, the drain current is what? 0. So both A and D satisfy this condition. Now you have to decide what is the shape. Will it be non-linear like this or will it be linear like this? Definitely it will be what? Non-linear. Because you know the MOSFET operates in saturation. ID is proportional to what? VGS minus VTH whole square. Or ID is proportional to what? VGS is what? VDD minus VSS and then minus VTH whole square. So look at how ID depends on VSS. It is not linear dependence, it is what? Square dependence. Okay. As VSS increases, VGS will decrease, then your drain current also will decrease. So as VSS increases, your drain current will increase, but not linearly, but in a non-linear fashion. So what is the correct option? It is what? Option A. Okay. So this is incorrect, this is incorrect. This is partly correct, but not completely correct. Okay. So when is the drain current maximum? When VGS is maximum. VGS is maximum when VSS is what? Minimum. When VSS is 0, you can say the drain current is what? Maximum. Okay. And as VSS increases, the drain current continuously decreases. Okay. Well, moving on to the next question. In the circuit shown, this is the circuit. Both the enhancement mode NMOS transistors, so there is one NMOS, there is another NMOS, have the following characteristics. So for both the transistors M1 and M2, the value of mu n Cox WL is what, this much. The threshold voltage is what, this much. Assume that the channel length modulation parameter lambda is 0. So indirectly they are saying there is no channel length modulation. And body is what, shorted to source. When body is shorted to source, there will be no this body effect. There will be no body effect. Okay. So the minimum supply voltage VDD, there is the supply voltage VDD needed to ensure that transistor M1 operates in saturation. So if you look at M2, for M2 gate is shorted toward drain. Yes, so M2 if at all it is on, will definitely be in saturation, because for M2 gate is shorted toward drain. Okay, but for M1 that is not the case, but we want M1 also to operate in saturation. In the question itself, it is clearly said that M1 should operate in saturation. For that, what is the minimum value of VDD? Okay, you see, whether both operate in saturation or both operate in triode, one thing is always true. What is that? Both transistors carry the same current. This, if there is what I1 and there is what I2, no matter what, I1 must be equal to what? I2. I1 must be equal to what? I2. What is this? VGS2. What is this? VGS1. Okay. Now both are operating in saturation, both are equally strong. Yes or no? This mu Cox WL, it is same for both transistors and both carry same current. Look at this. We have two transistors which are operating in saturation, which are equally strong and which carry same current. Do they not have the same overdrive voltage? Yes. So both are equally strong. Both are also operating in saturation. So the implication of these three things is what? That overdrive voltage will be same for both transistors. So VGS1 minus VTH is equal to what? VGS2 minus VTH. Okay. Now threshold voltage is anyway same for both transistors. VTH will get cancelled out. I can also say VGS1 equal to what? VGS2. VGS1 equal to what? VGS2. What is VGS1? 2 minus 0. So VGS2 is also what? 2 volts. I hope you get it. VGS1 is 2. So VGS2 is also what? 2. Okay. Alright. Now what is the voltage here? It is what? VED. What is VGS2? It is what? 2. So what is the voltage here? It is VED. Now what is the voltage at this point? This is VED. Then you go from plus to minus, subtract the drop. It is what? VED minus 2. Now please look at M1. So for M1 to be in saturation, VD must be greater than VG minus VTN. For M1, what is the drain voltage? It is VDD minus 2. For M1, what is the gate voltage? It is 2. What is the threshold voltage? It is what? 1. So from here, we get VD greater than 3 volts. So what is the minimum value of VD for which transistor M1 also will be in saturation? 3 volts. So what is the correct answer? It is what? 3 volts. It is completely based on the fact that identical transistors are equally strong transistors carrying same current and operating in saturation will have the same overdrive voltage. And since the threshold voltages are identical, even the gate to source voltage is identical for both transistors. Okay, so what is the minimum value of VED? It is what? 3 volts. Okay. Let's move on to the next question. A long channel NMOS transistor. So whenever they mention long channel transistor, long channel implies what? You can ignore channel length modulation. So that is an indirect way of saying that there is no channel length modulation. Channel length modulation will be significant when you have a short channel transistor. And generally for a long channel device, the reduction in channel length is very small compared to the original channel length itself. Okay, so that reduction can be neglected or ignored. Okay. Anyway, a long channel NMOS transistor is biased in the linear region. VDS, linear means what? It is the other name for triode. VDS is what? 50 millivolts and is used as a resistance. This is something we already know. MOSFET in triode can behave like a resistance, voltage controlled resistance. Which one of the following statements is not correct? So you have to choose or select the incorrect statement. Okay. If the device with W is increased, resistance, threshold voltage. Okay. So what is the effect of various parameters on the value of the resistance? Okay. So the point to understand is what this. Look at this value of VDS. It is what? 50 millivolts. Okay. Is it not a really small value of VDS? 50 millivolts is what? 0.05 volts, which is almost like 0. When VDS is really small and almost equal to 0, you know the MOSFET operates in deep triode. So this implies MOSFET in deep triode. If the MOSFET is in deep triode, what is the equation for the drain current? It is mu n Cox W by L times VGS minus VTH times VDS minus half VDS square. But in deep triode, this half VDS square can be neglected. Half VDS square can be neglected. Then your ID is equal to what? Mu n Cox W by L VGS minus VTH times VDS. And what is the resistance between drain and source? Ohm's law, it is VDS by ID, which is 1 by mu n Cox W by L times VGS minus VTH. So from this expression, you can easily pick the incorrect statement. W is increased. If W increases, resistance will decrease. Resistance decreases. This statement is what? Correct. Okay. If the threshold voltage is reduced, if VTH is reduced, then your overdrive voltage will increase. Then your resistance will decrease. Threshold voltage reduced, resistance decreases. This statement is also correct. Look at the C statement. Device length is increased. L increases. L will actually go to what? Numerator. L increases. Resistance also will increase. So C statement is also what? Correct. So the option must be what? D. Anyway, if VGS is increased, then your VGS minus VTH also will increase. Then your resistance will decrease. So this is what the incorrect statement. So what is the incorrect statement? It is what? Option D. That is the correct answer. Okay. Let's move on to the next question. For the circuit shown, this is the circuit shown. So we have seen such circuits many times during our course. Okay. So for the circuit shown, assume that the NMOS transistor is in saturation. So they themselves are saying, assume it is in saturation. The threshold voltage is what? 1 volt, and its transconductance parameter, that is what? This factor is what? 1 milliamp per volt square. Again, neglect channel length modulation and also a body effect. Under these conditions, the drain current ID will be how much? Okay. So what is this current? It is what? 0. So these two will be in series. So what is the voltage at this point? It is what? 5 volts. What is this current? It is also what? The drain current ID. What is the name of this voltage drop? It is what? VGS. Okay. Just a second. So this is what ID. So what is the drop across 1K? ID into 1 kilo ohm. So what is the voltage at this point? ID into 1 kilo ohm. Okay. So what is VGS? It is 5 minus ID into 1 kilo ohm. Now, because it is already given that the MOSFET is operating in saturation, assume that the NMOS transistor is operating in saturation. What is the equation for ID? Half mu n Cox W by L VGS minus VTH whole square. Okay. What is the value of mu n Cox W by L? It is 1 milliamp, which is 10 power minus 3 times VGS is what? 5 minus ID into 1K. 1K is what? Like 1000, right? So I can write 5 minus 1000 ID minus the threshold voltage is what? 1 volt whole square. So 2000 ID is equal to what? I think 16 plus 10 power 6 ID square minus 2 into 4 is what? 8000 ID. So again we get what? A quadratic equation for ID, and that equation is what? Like this: 10 power 6 ID square minus 10,000, which is 10 power 4 ID, and then plus 16 equal to what? 0. Okay. Let me find the two roots of this equation. So these are the two roots or the two values of ID. Obviously, ID cannot be two different values. You have to eliminate the invalid root. Okay. So for the two values of ID, let me write the corresponding values of VGS. Remember, VGS is what? This 5 minus ID times 1K. 8 milliamps into 1K is what? 8. 5 minus 8 is what? Minus 3 volts. And 2 subtracted from 5 is what? 3 volts. You know your VGS must be greater than VTH. And VTH is what? 1 volt. Okay. So minus 3 is not more than 1, but there is what? More than 1. So what is the correct value of ID? It is what? 2 milliamps. Your ID has to be such that VGS will be greater than VTH. Then only the MOSFET will be on and it can operate in saturation. Okay. Please look at the next question. Assuming that transistors M1 lower transistor and M2 the upper transistor, clearly both are what? NMOS transistors, are identical. So they are saying that both transistors are identical. That means what? They have same strength. They also have the same threshold voltage. Okay. And what is that same threshold voltage for both transistors? Is what? 1 volt. The state of transistors M1 and M2 are respectively. So you have to find the region of operation of each transistor. M1, what is it? M2, what is it? Here again, what is the constraint? Both the transistors are actually connected in series. So no matter what, the two currents have to be equal. So this is I2, this is what I1. So under all conditions, I1 must be equal to what? I2. I think for M2, it is very straightforward, because for M2, drain and gate voltage are already given. You can check the condition either for triode or saturation. Okay. So for M2 to be in saturation, Vd must be greater than Vg minus Vtn. For M2, Vd is what? 3. For M2, Vg is what? 2.5. Vtn is what? 5. 1. 3 greater than 1.5, which is indeed true. That means what? M2 is in saturation. Now let's find out the region of operation of M1. Okay. Let's find the region of operation of M1. So already M2 is in saturation. You see, let us assume M1 is also in saturation. Because for M1, we don't really know what is the voltage at the drain. Let's assume M1 is also in, saturation. Okay. Listen carefully. Assume M1 to be in saturation. Now, don't we have a case where we have two identical transistors carrying same current and operating in saturation? Then the overdrive voltage will be same for both. Even the threshold voltage are equal. That means VGS is also what? Same for both. Okay. So if you assume M1 to be in saturation, then VGS1 will be equal to what? VGS2. What is VGS1? It is what? 2 volts. Then this will also be 2 volts. Okay. Then this is 2.5. You have a drop of 2. The voltage at this point will be what? 0.5. Yes. Now VD1, that is the drain voltage of transistor M1, will be what? 0.5 volts. Now let's find out if this drain voltage of M1 satisfies the condition for M1 to be in saturation. For M1 to be in saturation, Vd must be greater than Vg minus Vtn. Vg for M1 is what? 2. Threshold is what? 1. So Vd must be greater than, in fact, we found that if M1 is in saturation, the drain is what? 0.5. 0.5 greater than 1. Is it true or false? Clearly it is what? False. So the condition for saturation is not satisfied. That means this assumption, it is what? Incorrect. What assumption? That M1 is in saturation. It is what? Incorrect, because ultimately the condition for M1 to be in saturation will not be satisfied. But M2 will be in saturation and M1 will not be in saturation, which means M1 operates in triode. So this means M1 will operate in triode or linear. So M1 in triode, M2 in saturation. So linear saturation, which is what? Option C. Understood? Alright, look at the next question. In the circuit shown below, that is what? This circuit, which again contains what? Two transistors M1 and M2. Both are what type? Both are NMOS transistors. The two NMOS transistors are otherwise identical. The W by L value of M2 is what? Twice that of M1. The two NMOS transistors are otherwise identical. That means what? That mu Cox value is same for both, but W by L is not same. Okay. Even threshold voltage must be identical, and it is what? Some 1 volt. Okay. And there is the usual, drain current equation that we already know. Okay. You have to find what? The voltage Vx. You have to find what? The voltage Vx. What is this Vx? It is the drain of M1. It is also the source of M2. Okay. Say for M2, gate is given, drain is also given, you can directly check the condition for M2 to be in saturation or triode. Yes. So for M2 to be in saturation, Vd must be greater than Vg minus Vth. For M2, what is the drain? 3.3. For M2, what is the gate? 2. Threshold voltage what? 1. So this condition boils down to what? 3.3 greater than 1, which is indeed true. That means M2 operates in saturation. Whatever be it, if at all M2 is on, M2 will operate in saturation. Okay. Now we should decide the fate of M1. Okay. For M1, what is the value of VGS? It is clearly 2 volts. Okay. This gate to source voltage of M2 will denote it by VGS2. Okay. So what is VGS2? It is 2 minus Vx. It is what? 2 minus Vx. For sure, this VGS2 it must be greater than Vth. It must be greater than 1 volt. That means Vx will be less than 1 volt. We do not know the exact value of Vx, but for sure, because M2 will be on, VGS2 must be greater than Vth. From there, we get this condition on Vx. Vx will be some value that is less than 1 volt. Okay. Now let us check the condition for M1 to be in saturation. What's the condition for M1 to be in saturation? Vd greater than Vg minus Vth. For M1, Vd is what? Vx. For M1, gate is what? 2. Threshold is what? 1. 2 minus 1. Which means Vx must be greater than 1 volt. So for M1 to be in saturation, this Vx must be some value which is more than 1. But we already know that Vx will definitely be some value which is less than 1. If Vx is already what? Less than 1, how come this condition be satisfied? It won't be satisfied. That means M1 cannot operate in saturation, then M1 will operate in triode. Yes, so this implies M1 will be in triode. So what is it so far? M1 operates in triode and M2 will be in saturation. Now we have to find what the value of Vx. The only thing we can do is what? Equate the two currents. Okay. Call this current I2, call this current I1. Equate the two currents, you should be able to solve for Vx. Okay, I'll just write the equation. I1 equal to what? I2. What is I1? Sorry. I1 is what? Current through M1 which is operating in triode, right? Yes. Will be mu n Cox W by L1 times VGS1 minus VTH into VDS1 minus half VDS1 square equal to I2. Right hand side we have what? I2. I2 is what? Current through M2 which is operating in saturation. Half mu n Cox W by L2 times VGS2 minus VTH whole square. So here also we can cancel out a few things. First mu n Cox will get cancelled out. Now in the very first line of the question, it is given that W by L of M2 is twice that of W by L of M1. So W by L2 is what? 2 times W by L1. Okay. So I think this and this can be cancelled out, and here 2 will remain, and this 2 and this 2 will get cancelled out. Okay. Now you have to write what is VGS1, what is VDS1, what is VGS2, like that. And then you should be able to solve for Vx. Okay, let me see if I can solve it. So what is VGS1? VGS1 is what? 2. Threshold voltage I think is what? 1 volt. Yes. So VGS1 is what? 2 minus 1 times what is VDS1? VDS1 is what? This drop, which is Vx. Okay. Minus VDS1 squared, which is half Vx square, equal to VGS2 minus VTH. What is VGS2? 2 minus Vx. 2 minus Vx minus 1 whole square. That's all. Again, we get a quadratic equation in terms of Vx. Okay. Anyway, Vx minus 0.5 Vx square equal to what? 1 plus Vx square minus 2 Vx. Okay. I think you'll get 1.5 Vx square minus 3 Vx plus 1 equal to what? 0. So let us try to solve this equation. 1.5 and 3 is what? 1. So what are the two roots of this equation? 1.58 volts and also 0.422 volts. But what is the condition on Vx? Definitely your Vx has to be less than 1. Okay. Because this is what? Not less than 1. Only this is what? Less than 1. So what is the final value of Vx? It is 0.422 volts. Yes. Moving on to the next question. Consider a long channel MOSFET with a channel length. Channel length is given 1 micron. Width is also given 10 micron. So what is the value of WL? 10 micron by 1 micron, it is what? 10. The device parameters are acceptor concentration. So this acceptor concentration, probably it is the doping concentration in the p-type substrate. Okay. 5 into 10 power 16 per cm cube. Electron mobility mu n is what? This much. Oxide capacitance per area, that is what? Cox is what? This much. Threshold voltage is already given, 0.7. The drain current ID sat for a gate voltage. So drain saturation current. So they are only telling that the MOSFET is operating in saturation for a gate voltage of 5 volts. Okay. All right. So I think here the circuit is not given. So you can assume that VGS is what? 5 volts. Okay. Let me write it properly. So you can write that VGS is what? 5 volts. And what is ID sat? It is half mu n Cox WL times VGS minus VTH whole square. Okay. Which is half into mu n is what? 800. Cox is what? 3.45 into 10 to the minus 7. WL is what? 10. VGS is what? 5. Threshold voltage is what? 0.7. And then square. You just have to find the value of this. Okay. 4.3 into 4.3 into 10, 5 into 3.45 into 800. So this is what I am getting, this 10 power minus 7. So the final answer must be in milliamps, okay. So 10 power minus 7, I'll write it as 10 power minus 4 into 10 power minus 3. So this is what the milliamp part, and this is what 25.52 milliamps. So what is the value of the drain current that we got? This much, 25.52 milliamps. 25.52 milliamps, okay. Let's move on to the next question. In the circuit shown, there is the circuit. V1 is what? 0. Where is V1? It is the gate voltage of this transistor. V2 is what? VED. V2 is the gate voltage of this transistor. The other relevant parameters are mentioned in the figure. In fact, for every transistor, the aspect ratio is what mentioned against the transistor. Okay, ignoring the effect of channel length modulation and the body effect, the value of I out. So you have to find this current. Okay, first of all, this is what a current mirror. This circuit, it is what a current mirror. So just do it systematically. This is the reference current source whose value is what? 1 milliamp. Okay, so this, it is like your IREF. Look at this and this, these two transistors, are they not in parallel? Both the gates shorted together, both the sources connected to ground. So both are connected in parallel. And even for this transistor, drain is what? Shorted to gate. So this transistor will generate the required VGS, which is then shared with this transistor. That is what will happen. Anyway, the point that you should know is what? Let me mark the gate currents as well. Every gate current is what? 0. So what is this current? It is what? 1 milliamp. So what is the ratio of these two currents? It is equal to what? Ratio of their aspect ratios. This is what? 3, this is what? 2. So the ratio of the aspect ratios is what? 3 by 2 or 1.5, which means this current will be what? 1.5 times this current, and that is how much? 1.5 milliamps. And that is what? 1.5 milliamps. Okay. Now look at the remaining transistors. Please look at this and this. Are these two transistors connected in parallel? Not really, because what is V1? It is 0. What is V2? It is what? VDD. What is V2? It is what? VD. So both the sources are, so this source and this source both are connected to what? Same point. So we can say both the sources are at same potential, but same is not the case for both the gates. Yes, so both the sources at same potential, but both the gates are not at same potential. That means this VGS and this VGS are not equal. This VGS and this VGS are not equal. So the two transistors are not really in parallel. Okay. The other point is what? See, one thing that will happen is what? This 1.5 milliamps will get divided between these two transistors. Okay. Had they been in parallel, then the ratio of the currents will be equal to what? Ratio of their aspect ratios. But here the two are not in parallel. Okay. This gate is what? VED. This gate is what? 0. VED generally is what? A large voltage. VDD generally is what? A large voltage. Let me draw this thing separately. So if this is what? Some 1.5 milliamps. Okay. Let's say this is what? 2.5. This is also 2.5. So this aspect ratio is what? 5. This aspect ratio is also what? 5. Okay. Now both are in parallel. Do you agree with that? This is 2.5, this is 2.5. Both the gates are at same potential, both are in parallel. Okay, so this will be half the current, this will also be another half the current, 0.75, 0.75. Let's say you keep on increasing this and you keep on reducing this. As you keep on increasing this, more current will flow in this transistor. Yes or no? More current will flow in this transistor, and as you keep on reducing this, less current will flow in this transistor. Yes, so there will be what? Imbalance. If the two gates are at same potential, then the two currents will be equal. But if one gate is what? Increased above the other gate, then one transistor will carry more current compared to what? The other transistor. Now as the two gate voltages move away from each other, even the imbalance will increase. Yes, now this will go to an extreme, which is what? Some 5 volts. This will go to what? 0. Then what happens is, this will almost turn off and only this will be on. Then this entire current will only flow in the left side transistor. You understood, right? Yes. So there will be a great imbalance, which will lead to what? Current steering. So what is current steering? This entire current is being steered into what? Only one transistor. Yes. Had the two gates been at the same potential, this current would get divided equally. But here, because of the great imbalance between the two gate voltages, even the two drain currents will have that large imbalance. And what happens is, this entire current will only flow through what? One particular transistor. Which transistor? That transistor which has a very large, or which has a relatively larger gate voltage, will carry almost all the current. You understood, right? Yes. So here, the left side transistor, the gate voltage is what? 0. Right side transistor, the gate voltage is what? VED. So you would expect that the entire current will only flow through the right side transistor, and the left side transistor will carry what? 0 current. Okay. So what is this current? It is 1.5 milliamps. Again, this current, both are 0. So this current is also what? 0. So this current will be what? 1.5 milliamps. Again, if you look at these two transistors, these two PMOS transistors, are they not in parallel? Both the gates shorted together, both the sources also shorted together. Yes. So these two are in parallel. So whenever PMOS transistors are in parallel, and of course they will operate in saturation in a current mirror, the ratio of the currents will be equal to what? Ratio of the aspect ratios. So I out by 1.5 milliamps will be equal to what? Ratio of their aspect ratios, which is 40 by 10, that is what? 4. So what is I out? It is 6 milliamps. What is I out? It is what? 6 milliamps. Okay. So what is given in this question? An enhancement MOSFET of threshold voltage 3 volts. So the value of VTH, that is the threshold voltage, it is what? 3 volts, is being used in the sample and hold circuit given below. So what is this circuit? It is a sample and hold circuit. So any sample and hold circuit will have two modes or two phases. So during the sampling mode, this transistor, which will behave like a switch, will be closed, and whatever is the input voltage, that will go to the capacitor. And during the holding mode, that voltage which is held on the capacitor will be quantized, will be converted into what? A sequence of zeros and ones. Once that conversion is complete, then again you pick another sample of the input, again you hold it on the capacitor, and then you quantize it. So this thing will continuously happen in a periodic fashion. Okay. So any sample and hold circuit will contain what? A switch which is implemented using a transistor, and then a capacitor to hold that voltage during the interval where the analog value will be digitized. Okay. So this transistor behaves like an on and off switch. That is the fundamental point. Assume that the substrate of the MOS device is connected to what? -10. Okay. See, threshold voltage is 3 volts. So this implies that the transistor is what type? It is NMOS. NMOS transistor, the substrate is what? P type. And generally, to reverse bias, the source body and the drain body junctions in an NMOS transistor, that P type substrate should be connected to what? Most negative available supply voltage. So this minus 10 volts, I believe, it is what? That most negative available supply voltage, and that is what the substrate is connected to. So this will ensure under all operating conditions, the source and drain body junctions, the source body and the drain body junctions will always be reverse biased. Okay. Now, if the input voltage Vi, this is what the input voltage Vi. So this is the analog value that is being sampled, okay, and then converted into what? Digital. Okay. So this Vi can be any value in the range plus 10 and minus 10, or minus 10 to plus 10 volts. Then the minimum and the maximum values of Vg. What is this Vg? It is the voltage applied at the gate. So Vg, it is what? The voltage applied at the gate, required for proper sampling and proper holding respectively. So for proper sampling, what is the minimum value of the voltage that must be applied at the gate, so that you are able to sample any value of input that lies in the range minus 10 to plus 10. And then what is the maximum value of Vg, such that so during the holding cycle or the holding mode, the switch will be closed. During sampling mode, the switch must be closed, and during holding mode, the switch must be open. If I said closed, then I'm sorry. During holding mode, the switch must be open. Okay. So the thing is what? This. So this Vi will go to the capacitor. Yes. And the voltage across the capacitor can be anything in the range minus 10 to plus 10. Yes. So this, I'll call it what? Vc. So Vc, which is the voltage across this, holding capacitor, can be anything in the range minus 10 to plus 10. Okay. And then obviously this thing where the capacitor is connected, you can assume it is what? The source of the transistor, and this is what? The gate. And what will decide whether the MOSFET switch is open or closed? It is the value of VGS. I repeat, it is the value of VGS that will decide whether the MOSFET switch is what? Open or closed. It should be open during holding. It should be closed during what? Sampling. Okay. All right. Now the voltage at the source is same as what? Voltage across the capacitor, and it can be anything between minus 10 and plus 10 volts. Okay. Now for proper sampling, the switch should be closed. In other words, the MOSFET must be on even in the worst case. Listen to this carefully. For proper sampling, switch should be closed even in the worst case. Yes, what will decide whether switch is open or closed? It is the value of VGS. Now in the worst case, VGS will become maximum or minimum. Worst case, yes, for sampling, VGS will be minimum. Yes, even when VGS is what? Minimum, still during sampling, the switch should be closed or the MOSFET must be on. So here, what is the meaning of this worst case? VGS becomes minimum. Even when VGS becomes minimum, then also the MOSFET must be on or the switch must be closed. Okay. Now, Sai is asking, so substrate will be then transistor is PMOS or NMOS. If substrate is plus 10, then the substrate is what? N type. Then the transistor will be PMOS. But here the substrate is what? Connected to minus 10. Even before that, if you look at the threshold voltage itself, it is what? Positive. Positive threshold voltage means what? The transistor is NMOS. Even from this you can conclude that it is what? NMOS. Okay. So VGS should become minimum. Even when VGS becomes minimum in the worst case, still the MOSFET must be on. So VGS min will be equal to what? VG minus Vs max, and this should be greater than VTH. What is Vs? It is same as what? Voltage across the capacitor. Now the capacitor can hold any value in the range minus 10 to plus 10. VGS will become minimum and the source is what? Maximum. And the maximum value of that source is what? Plus 10. So VG minus 10 must be greater than the threshold voltage, which is what? 3. So this gives us what? VG greater than 13. So for proper sampling, the gate voltage should be at least 13 volts. At least 13, that means what? Minimum value of the gate voltage for proper sampling under all conditions is what? 13 volts. Is what? 13 volts. I think right here we can choose the correct option as what? C, because no other option. The minimum value of VG during sampling is what? 13. But anyway, we'll also find the maximum value of VG for proper holding. Okay. See, what is the requirement during holding phase? During holding phase, the switch must be open or the transistor must be off. Okay, I'll just write it. During holding, switch must be open. Again, let me write, even in the worst case. Switch must be open, it means what? Transistor must be off. Yes, that means your VGS must be what? Less than VTH. Even if VGS is what? Maximum, even that maximum value of VGS should be what? Less than VTH. Then any other value of VGS will definitely be less than VTH. Then during holding, the transistor will always be off. This is the logic. Okay. So this time, what is worst case? The same VGS, it becomes what? Maximum. So in the worst case, even if VGS becomes maximum, still that maximum value of VGS should be what? Less than VTH. Then only the switch will be open or the MOSFET will be off. Okay. Look at this. So again, when will VGS become maximum? When source is what? Minimum. Okay. So VG minus Vs min should be less than VTH. For proper sampling, it must be greater than VTH. Even the minimum value of VGS must be greater than VTH. Then for all values of VGS, the MOSFET will be closed or on. That is during sampling. But during holding, all values of VGS, the MOSFET must be off. Even for maximum value of VGS, the MOSFET must be off. That is why I wrote VGS max must be less than VTH. Now for VGS to be maximum, Vs should be minimum. What is the minimum value of Vs? It is what? Minus 10. Okay. So Vg minus 10 less than 3, which is same as what? Vg less than minus 7 volts. So for proper holding, the gate voltage should not be greater than minus 7. So that is the maximum value of the gate voltage. Even the question talks about what? Maximum value of Vg for proper holding. So Vg less than minus 7. Minus 7 is what? Max. So this is what? Vg min, and this is what? Vg max. And this is for sampling. This is for holding. I hope you get the point. Okay. Moving on to the next question. For the transistor M1 in the circuit shown in the figure, mu n Cox is what? 100 microamp per volt square. So for this transistor, mu n Cox value is given. Aspect ratio is what? 10. Okay, mu n you know is what? Mobility. Cox is what? The oxide capacitance per unit area. W is the width, L is length. These are all trivial data. The channel length modulation coefficient is what? Ignored. That means lambda is what? 0. If the gate to source voltage VGS is what? 1 volt. To keep the transistor at the edge of saturation. So when the value of VGS is what? 1 volt, then the transistor operates where? At the edge of saturation. You know, at the edge of saturation, at EOS stands for what? Edge of saturation. VD equal to what? VG minus VTH, or VDS equal to what? VGS minus VTH. So VD equal to what? VG minus VTH. So the question is what? The threshold voltage of the transistor is how much? You have to find the value of the threshold voltage. It is quite simple. So because it is given that the transistor is operating at the edge of saturation, this equation will be true. VD equal to what? VG minus VTH. So what is the voltage at the gate? Because VGS is 1, gate will be what? 1. So it will be what? 1 minus VTH. And that is same as what? V out. So what is V out? It is 1 minus VTH. So what is this? It is the drain current. There is also what? The same drain current. And you know, at the edge of saturation, ID is equal to what? ID sat. What is ID sat? Half mu n Cox WL times VGS minus VTH whole square. Now the same drain current is also what? The current through this resistor, which can be written using what? Ohm's law. Which can be written using what? Ohm's law. 3 minus V out. But V out is what? 1 minus VTH. 3 minus 1 plus VTH by the resistance, which is what? 20 kilo ohm. Okay. Okay, let me write it this way. 3 minus V out by RD. Now let's substitute the values. Okay. V out is what? 1 minus VTH. So 3 minus 1 plus VTH. 20 kilo ohm is what? 2 into I think 10 power 4. And then half into mu n Cox is what? 100 micro, which is 10 power minus 4. W by L is what? 10. And then VGS is what? 1 minus VTH whole square. Now the only unknown in this equation is what? VTH, which you can easily find. Okay. I think again a few terms will cancel out. This 2 and this 2 will get cancelled out. 10 power 4. This also will get cancelled out. What else will get cancelled out? I think that's all. Okay. So this is what? 2 plus VTH, and this is what? 10 plus 10 VTH square minus 20 VTH. So 10 VTH square minus 21 VTH, correct? Plus 8 equal to what? 0. So let's find the two roots of this quadratic equation. (10 minus 21 and 8). 10 minus 21 and 8. 1.6 and 0.5. These are the values of VTH. See what is given in the equation, that when VGS is what? 1 volt, it is operating at the edge of saturation. That means definitely MOSFET is on. So this 1 volt of VGS is what? Definitely greater than VTH. And if VTH is what? 1.6, VGS will be less than VTH. So this cannot be the root. This is the actual answer. So what is the value of VTH? It is 0.5 volts. Okay. Let's move on to the next question. I think another 2 questions are left. Only these 2. Okay. Consider an ideal long channel N channel MOSFET with gate length 10 micron. That means L is what? 10 micron. And then width is what? 100 micron. So length is 10, width is what? 100. So from this we can say the aspect ratio W by L is what, 10. The product of electron mobility mu n and the oxide capacitance Cox is what, this. So mu n Cox is already given 1 milliamp per volt square. Threshold voltage of the transistor is what, 1 volt. For a gate to source voltage VGS equal to 2 minus sin 2t. So this VGS, it is not a constant value. It is going to vary with time, because sin 2t will obviously vary with time. Even VGS will vary with time. And drain to source voltage, that is VDS, is what, 1 volt. VDS is what, fixed. So here VDS is what, fixed and equal to what, 1 volt. Whereas VGS is what, 2 minus sin 2t, which is what, variable. Now you know the sine function will vary between -1 and +1. So what is the range of VGS? What is the range of VGS? If sine function is 1, 2 minus 1 is what, 1. If sine function is -1, then 2 minus -1 is what, 3. So VGS can be any value in the range 1 to 3 volts. Minimum value of VGS is what, 1. Maximum value of VGS is what, 3. So given these values, the question is what, the maximum value of the drain to source current, that is what, the drain current is how much. So what is the equation? It is to find the value of ID max, that is the maximum drain current. Now the MOSFET, for maximum drain current, you should decide whether it should operate in triode or saturation. What was the earlier point? Earlier I said, if the overdrive voltage or VGS minus VTH is what, fixed, then maximum current will flow in saturation. But here, what is VGS? It is not a fixed value. It can take any value in a certain range. Yes, had the overdrive voltage been fixed, then you can definitely say that maximum current will flow if at all the transistor operates in saturation. So do not apply that logic here. Okay. See, we'll just quickly investigate both the possibilities. Okay, if at all it operates in triode, what is the maximum current? And if it operates in saturation, then what is the maximum current? So in both triode and saturation, we'll find the maximum possible current, and between those two maximum values of current, we'll pick the maximum value. That is the final maximum possible value of the drain to source current, or simply the drain current. Okay, look at this. If you take the MOSFET to be operating in saturation, then your VDS must be greater than VGS minus VTH. But VDS is what, fixed and equal to what, 1 volt. VGS is what, variable. VTH is again what, 1 volt. So the point is what, if at all the MOSFET operates in saturation, then your VGS cannot be more than 2. VGS should be less than 2. Then what is VGS minus VTH? If VGS is what, less than 2, then VGS minus VTH will be less than 1. So what is this 1 volt? It is the maximum value of the overdrive voltage. Yes. So in saturation, when will the drain current be maximum? When the overdrive voltage is what, maximum. Okay. Half mu n Cox W by L times the square of the maximum value of the overdrive voltage. What is that maximum value of the overdrive voltage? It is what, 1 volt. Half into mu n Cox is what, 1 milliamp per volt square. If you want, I can write the units. W by L is what, 10. Maximum value of the overdrive voltage is what, 1. Square of it is what, also 1 volt square. So the maximum value of the drain current, if at all the transistor operates in saturation, is how much? It is 5 milliamps. In the same way, let us find the maximum possible drain current when the transistor operates in triode. Okay. So this time let's say the MOSFET operates in triode. So in triode, given that VDS is what, fixed, when will the drain current be maximum? When the overdrive voltage is what, maximum, okay? So before that, for triode, VDS must be less than VGS minus VTH, and VDS is what, 1, VGS, I'll write it as VGS only, and then minus VTH is what, VTH is what, 1. So from here we get VGS greater than 2. VGS greater than 2. So if VGS is what, greater than 2 volts, then the MOSFET operates in triode. And what is our range of VGS? 1 to 3. 1 to 3, definitely there is a range of values which will satisfy this condition, that is VGS greater than 2. Yes, that means 2 to 3, VGS from 2 to 3, MOSFET will be in triode. VGS from 1 to 2, MOSFET will be in saturation. That is the point, okay? Now, for the drain current to be maximum, your VGS minus VTH also should be maximum, okay? VGS should be greater than 2. What is the maximum value of VGS? It is 3. So in place of VGS you write 3. So it is what, 3 minus 1, it is what, 2 volts. So if the MOSFET operates in triode, then the maximum overdrive voltage will be what, 2 volts. VGS should be any value greater than 2. And our range of VGS is what, 1 to 3. So for VGS minus VTH to be maximum, even your VGS must be maximum. And that is what, 3. 3 minus 1, maximum overdrive is what, 2. Now let's find ID max, which is mu n Cox W by L times VGS minus VTH max times VDS minus half VDS squared. Again, what is mu n Cox W by L? It is, mu n Cox is what, 1 milliamp per volt square. W by L is what, 10. Now VGS minus VTH maximum is what, 2. And VDS is what, 1. So 2 into 1 minus half into 1 square. Just find the value of this. Half into 1 square is what, half. 2 minus half, what is 2 minus half? 1.5. So 1.5 into 10. So this is also what, volt square. So this volt square and this volt square will get cancelled out. 1.5 into 10. So what is the value of ID max? It is what, 15 milliamps. So if the MOSFET operates in triode, then the maximum possible drain current is what, 15 milliamps. And if the same MOSFET operates in saturation, then the maximum current is what, only 5 milliamps. So which maximum current is maximum? So in which case the maximum current is higher, clearly in triode. Yes. So if you think it is 5 milliamps, it is what, incorrect. What is the correct option? It is what, 15 milliamps. Okay. Because here VGS is not fixed. VGS is what, variable. Had VGS been fixed, then maximum current will flow in saturation for sure. But that is not the case here. Okay. So what is the correct answer? It is 15 milliamps. And what is the region of operation? Triode. Okay. So we have finally come to the last question. I think this is very straightforward. In the circuit below, what circuit is this? This is what, the popular current mirror circuit. Okay. The voltage VL. So probably this voltage is what, VL. So you have to find the voltage VL. Okay. So what is this current? 0. What is this current? 0. So what is this current? 0. So what is this current? It is 1 milliamp. Okay. And then this and this both are in parallel. These two PMOS transistors, they are in parallel. The ratio of the currents will be equal to what? Ratio of their aspect ratios. If this is 1 milliamp, then this will be 10 milliamps. Okay. 10 milliamps. Again, this current, everything is 0. So even this current will be what? 10 milliamps. Okay. And by the way, this all are in parallel. All the gates shorted together, all the sources shorted together. So the three PMOS transistors at the top, all three are in parallel. So the ratio of this current to this current will be equal to what? Ratio of their aspect ratios. So you should be able to see that this current will be what? 7 milliamps. Okay. Now you come to this transistor and this transistor. Both are what? NMOS transistors. This one, both are NMOS. Again, these two are connected in parallel. So the ratio of these two currents will be what? Ratio of their aspect ratios. For this, the aspect ratio is what? 5. For this, it is what? 10. That means this current will be what? Half of this current, which is what? 5 milliamps. Okay. Now, if you look at this particular node, at this node 7 milliamps is incoming, 5 milliamps is what? Outgoing. So the remaining current will also flow away from the node. So what is this current through this 1 kilo ohm resistor? It is what? 2 milliamps, which will result in a drop of what? 2 volts. So the value of VL is what? 2 volts. This is a simple problem, which is based on the fact that transistors connected in parallel operating in saturation, the ratio of the currents is equal to what? Ratio of their aspect ratios. So this completes the discussion of all the problems related to MOSFET DC analysis. Okay, so I'll see you in the next session. Thank you.